So today is our pleasure to have with us in our weight seminar our visitor for this week, David Beltran. He is like Ramón y Cajal, tenure track tenure track professor there in Universitat de Valencia. Previously, he was working in Wisconsin, Madison, and in Beckham, in Bilbao, and he studied there in Birmingham. And I had like the pleasure of like working with him in the bus. And now today he will talk about helical maximal functions. And so, well, yeah.
Thank you, Christian, for the nice introduction, and thank you everyone for waiting. Yeah, now I'm nervous, right? So, ahora. Vale. So yeah, I'm going to present some results on the helical maximal function, which is an object I'm going to introduce now, and for the ones that were yesterday at the other seminar, it already showed that. And I'm going to report two joint works. The first one, the older one, is with Xiaoming Guo, Jonathan Hickman, and Andreas Seeger, and then there's another more recent result, which is joint work with Jennifer Duncan and Jonathan Hickman. So it's a subset of these people, these names will appear. Okay, so the setup which I'm going to be working with is, let's take gamma is going to be a non-degenerate curve, and I'm only going to be working in 3 dimensions, but I'm going to start by putting the setup in a general context. And by non-degenerate curve, what I mean is that the first derivatives, if he is the ambient dimension of the parameterization for gamma, they span R. Okay, and here the classical example is in R2 we take a circle, in R3 we take a helix. So in R3 it starts with non-vanishing curvature and torsion, and in any dimension the moment curve would be the prototypical example. And given these curves, we can consider the following two operators. One of them is the average along one of these curves. So what we do is we translate the curve so that it's like center at a point X. That's what this means. So we do convolution of a measure supported in the curve with a function, and we are going to be dilating that curve, okay, with a parameter t, and we are going to consider the maximal function associated to those dilations, and then LP bounds on this maximal function, they would imply an almost everywhere convergence result for the averages to the original function in the relevant LP space. And the conjecture here is that this maximal function should be bounded for all p greater than the dimension. And this has been a conjecture that has been around for a while. This all started with the work of Stein for hypersurfaces, but this is the version for curves, which is harder. And in dimension 2, this was solved by Bourgain, is the celebrated result of the circular maximal function. And in dimension 3, prior to our work, there was the following result that for p greater than 4, the work by Pramanik and Seeger in 2007 was giving a partial result that was depending on some other conjecture. That other conjecture was later solved by Bourgain and Demeter. So then joining deep with this conditional result, then they could go down to p equal 4. Okay, strict. But indeed in 3 dimensions, the result that one expects is p greater than 3. And so the first theorem I want to present is that the conjecture actually holds for p equal to 3, and one can push down the exponent between 3 and 4 and cover the missing range. Okay, and this was obtained with Guo, Hickman, and Seeger, and it was independently obtained by Ko, Lee, and O. Okay, and there are further results in higher dimensions. Also, Ko, Lee, and O, they obtain later partial results in higher dimensions. Look that the conjecture should be p equal d. They obtain it for like twice the dimension, so there's still a missing gap. And in a way, their results, they are of the type of these Pramanik-Seeger results. Then the techniques are somehow reminiscent of that. There is no weak type estimate at the endpoint. The example, the classical example, like in the circular case, the Stein examples, like show that fits. Okay, with a function that is like a kind of like with a log in the singularity.
Yeah.
Yes.
You go back to the, so that I understand the conjecture. So the previous slide.
Yes. I know. Sorry, I have these many pauses. Yeah.
So the conjecture is for which gamma?
So is any in dimension.
The other question was
The gamma is any non-degenerate curve. Okay.
And the key, QFS.
The QFS, this is just this S is supported in an interval near the origin or something like that. Yeah.
The conjecture would be for.
Yeah. Yeah, it's supported here in this in the interval of parameterization. Like a cutoff function is smooth enough. Yeah. Okay. So and then the second result I want to present is that typically the LP bounds for the maximal function, there's a second version of them, which are called the LP improving bounds, and is to ask whether if we start with an LP input function, we can get some sort of like a smoothing gain or some extra integrability, and the output is in LQ. Okay, for this kind of inequality to hold, by a scaling argument, we cannot aim it for the whole supremum for all times, because that's by a scaling that only admits LP bounds. But if we restrict to the local version, then LP to LP bounds are available. And we can formulate a similar conjecture here in this in any dimension. And that the numbers they don't really matter, but is the classical NAP example for the ones that know about Fourier restriction theory. It tells you that this point should be a triangle, and this should be the key point. Okay. And in dimension 2, this is already old work by Slack, and later there are other proofs by Slack and Sok and Sanjugli concerning endpoints. And the other result I want to present from last summer is that the LPLQ conjecture also holds for the equal to 3. And when I mean that holds, is that it holds in the interior, and it is still open what happens at the end. Okay, in this case.
What is the point?
Yes, because if the T is for all greater than 0, okay, then this operator by scaling can only satisfy LP to LP bounds. Because if you just dilate your function and then you take, instead of f, you take f of lambda x, then you just see if this inequality is invariant under that scaling, and that forces the Q and the P to be the same if you can take all possible times. Okay, so then you need this condition in order to have LP to LP bounds. Yeah.
Can you comment a bit more on the boundary of the triangle?
Yeah.
Conjecture versus theorem.
In the sorry?
Conjecture versus theorem.
Okay, in the boundary of the triangle, okay, here is the diagonal bounds, no? So in the diagonal bounds, they are already the previous results. Okay, so then here we are not obtaining anything on this boundary. All that we obtain is in the interior.
The conjecture does not predict that.
The conjecture, there is no example at the moment ruling out that there could be bounds there. Okay.
So the endpoint is not weak type, it's Q3. That Q3 is a weak type estimate or not?
Is not weak type estimate.
Okay, okay. So you need the interior.
Is not weak type estimate at this endpoint. Okay.
The new one. So the Q3 is new of the.
Yes, because so for the Q2 cannot be weak type.
Okay.
But this part here could be even a strong type.
Okay.
As this.
Okay, I see.
Okay.
Including Q3.
Including Q3.
Okay.
Yes. Okay. And indeed, in dimension 2, this is the result by Sanjugli. It tells you that this is the result. Okay. So I'm going to try to present. I wanted to focus on the LPLP result, but for that I'm going to also explain the other one. So even for the global operator that Show has asked me about the t greater than 0, for all intents and purposes, we always study this between 1 and 2, because there are nowadays standard techniques that if you have these bounds for the local operator, by Littlewood-Paley theory, they can be all the scales put together. So let's forget about the global guide. Then a second standard reduction is that, okay, we are going to treat these objects by Fourier analysis. So when treating it by Fourier analysis, we are going to just focus on a function which is band limited, and we are going to fix the scale at which is band limited. And then if I can obtain for these ones, here I take a piece near the origin and then all the diagonal pieces. Okay, and I obtain for these functions an inequality which has this geometric decay with a little epsilon. Then I can sum trivially in K, so I'm good, right? So this is this implies the former one, no? And the second one is that the third one is that I have a maximal function, and just by doing this standard Sobolev embedding type argument, which is just fundamental theorem of calculus and Helder inequality, we can effectively replace a supremum in time by a product of a function and its derivative, and a product that is in the right with the right p. So to all intents and purposes is replacing it by 1 over p derivatives, and a derivative of this average is like the average with the size of the frequency scale. So we lose this factor, so we need to win over that factor. Okay, so we can reformulate our theorem as a new goal, and the new goal is that for 1 over p and 1 over q in that region where we expect all the boundedness, right? We want to that when we integrate in time the averages and take the space norm, then we beat the loss by the Sobolev embedding, and then we have the extra epsilon to get the summability decay. Okay, so that's the real goal. Okay, and these are typically called local smoothing estimates, because when there is no integration in time, imagine you just take the average, like at time equal to 1, one can study what are the Sobolev estimates for those guys, and these Sobolev estimates, they can be at most the best decay that one can obtain is 1 over q. That just comes from an example which would be taking a neighborhood of the curve. Okay, it's not a difficult one. So these are, we need to gain over these fixed time estimates, okay, by the integration given in time. And for context, that is typically referred to local smoothing estimates. Okay, so I'm gonna quickly revisit what happens in dimension 2, because there the setup is cleaner and easier, and that will give a flavor of the type of techniques that are gonna be used later. So the average, I'm gonna start by just looking at what happens at a fixed average, and then we are gonna look at what happens when we integrate in time. Okay, so for fixed average, this is given by a convolution of the measure supported in the curve. So I could look at what happens on Fourier side. You know, and on Fourier side, this is the Fourier transform of my measure, and is given by this oscillatory interval. And we are aiming to get the best possible thing, as I said, is the decay is 1 over p for some p depending on the dimension. No? And this is an oscillatory integral. So when I want to study L2 bounds for the average, I could go by Planck L2 Fourier transform, study directly what is the L infinity bound of this side. Okay, so then we know that the method of Wagner-Korkut will give us what is the rate of decay for that. And for this, we need to look at the stationary points for the phase function, how the phase function behaves. Okay, that's typically how one gets L2 bounds. And then L infinity bounds, they are for free, because this is an averaging operator, no? So they are bounded in an infinity, these are one kernel, no? It's an average. So so then one combines them to an L infinity, then we get some LP bounds in between, and maybe one needs to break it into pieces and look for some LP orthogonality. That's a little bit the kind of games that go around here. And if we start with the parabola, for instance, or you could think of a circle. I'm just writing here this parabola because computations are easier or nicer. Let's say, then we know that the first two derivatives are span, right? So the worst that can happen is that I need the derivative of the phase, that the first one can vanish, and then I have to use the second derivative. Okay, but that's going to be both of them, they cannot vanish simultaneously. No. So then Van der Kolk lemma immediately gives me that then the decay rate, it goes with the second derivative. Okay, so that's a minus k over 2 on L2. This is bounded in L infinity. That gives a minus k over p, which is the best that one can obtain. So the fixed time average for the two-dimensional case is very elementary. But what about when we integrate in time? When we integrate in time, we want to win over that. No. So now I have the t variable is now playing a role. No? So if I also try to do the same game, try to study this on Fourier side. Now I consider not just Fourier transform in X, but also Fourier transform in time. Okay, so then I get this new oscillatory integral, which now incorporates this Fourier transform in time. So now I have two parameters, the S coming from the parameterization and the T, no? For my multiplier. So I look at the critical points where this is stationary. And now it's giving me the points from before, okay? This equation that was coming from before, but I have the extra one coming from derivative with respect to t variable. So when these two vanish, now I'm in 3 dimensions. It's not I'm in the plane because I have the psi variable and I have the tau variable. I have 3 Fourier variables. And one sees that the solution of this is now in R3 is a whole cone. Okay, so I have a whole cone of singularities where first derivative of the phase function is where I have a stationary points. No? But away from that cone, things they behave okay. No, so the real difficulty is in a neighborhood of this cone. And because I'm having a scale, I can even quantify what is the cases in which I have decay. No? So then here I'm going to have to use second derivatives. No, that's what happens because I have critical points, so I have to use second derivatives. Okay, and then the question is, I only have in the S variable, like for a fixed psi, this is the bad S. Okay, this is the bad range of integration in this oscillatory integral. Okay, but then if I want a global estimate, as soon as I move, despite I can localize where things behave bad, if I have a global estimate, if I move psi all over, the S moves all over. So there is no improvement in the S variable. However, if I was looking for a fixed psi, I only need to focus on a very small interval. Okay, so this doesn't improve at infinity, but if I were breaking this what happens in the singular cone, in the S parameter, I'm breaking things into little pieces, then is an average over a smaller region, so it improves the infinity bound. So if I combine the L2 analysis with the L infinity bound, then I get that for each of these small pieces, the gain coming from L2 extends to all P. Okay. And then the question is how to access these small pieces where I have an improved estimate. If I can do it in a better way than trivial triangle inequality or triangle inequality plus some Cauchy's bars or something like that. No? And so this is to illustrate the picture. No, these small pieces corresponds to when we are in the singularity around the cone. We are breaking this into these plates. No, and for each plate we have an improved estimate. So is there some orthogonality going on? No? So on L2 that would be very easy, but on LP orthogonality is a harder problem. No? That would be the picture. So so there have been 2 leading approaches to how to access those pieces. One of them is through a square function estimates, in which one wants to control the LP norm of the part which is near the cone by the LP norm of the square function adapted to those small pieces or to those plates. Okay, this was introduced by Maximal in the 90s, and the key point here is to do it with no loss. Okay, if this was in L2, this would be immediate, right? And then the question is to do it with no loss for other values of P. And it was conjectured that for L4 should be possible. And then this was recently solved by Wood, Wang, and Zhang. Okay. For the maximal estimate, we don't need that much. We don't just need a little bit, right? But for the sharp local smoothing, this would be the optimum. So for the maximal estimate, we only need to, in case of the circle, we only need to win an epsilon over the fixed time estimate. So then any non-trivial local smoothing works. So one doesn't need to get this perfect power, but some improvement over trivial triangle inequality and Cauchy's bars would make the job. Okay. And this argument is very efficient because once you have that, one can access the pieces in a really good way through weighted estimates. This might show up later, and then there is no loss in the rest of the arguments. Maximal and so develop a very, very robust method. And there's been another competing approach, which was introduced by Wolf in the 2000, which is one in which the LP norm here and the little L2 norm, they are flipped. Okay, so so this would imply this one by Minkowski. Okay. However, this can hold in a larger range. So that's why this one is still known. Okay. This doesn't have interaction of pieces anymore. The LP norm is inside. So then you only estimate the pieces, right? Here there's still some interaction, which can still be used later to do good things. And the good things that this interaction gives you is that then there is no other loss in the argument. That's how it's used. In here, because we have decoupled completely the pieces, then when we want to put them together later on, there's a little loss in the argument because we need to put them together. We need to go from this little L2 to little LP, so that at L infinity we can put them together. At little L2 we have orthogonality, so then we can do it in the intermediate piece. But for that we need to lift it, and when we lift it, we lose in the number of pieces to the Holder exponent. Okay. However, because this falls in a larger range, this loss is still admissible for a work problem, and one still can obtain good results for when P is larger than 1/6. So at 6 is still giving a sharp argument. So there are these two approaches, and this one is stronger, but this one is still very useful. Okay, or depending on the problem. And then there's a third approach, which is using these multilinear Fourier restriction estimates. So these bilinear estimates, they are of the type that instead of when we have two pieces interacting against each other, if they are appropriately separated, one can get a sort of very good L2 based estimate, which improves over the linear one, which would be the Stein-Thomas estimate for Fourier restriction for the people who are familiar. So these bilinear estimates, they were used to prove square function estimates in the past, and make progress in that problem. That was work of Tao Vargas. But where they also play a very good role and quite a sharp role is in the problem of LP to LQ bounds for these maximal functions. So and the benefit of this is that in here the linear estimate would be this Stein-Thomas Strickhardt estimate. Okay, and this will give for the circular maximal function, this is of no use. However, if one has a bilinear estimate, this bilinear estimate gets improved because we can lower down the exponent, so which means going up here. Okay, and when one goes up here, it is possible to hit this critical line if one interpolates with something good over here. It could be even something here, it doesn't matter, right? But from the Strickhardt estimate, we are already in this line, so we cannot hit it, which is when it's critical. So these bilinear estimates can be used to hit this, and then one can get this point, okay, by interpolation. So they were fundamental in studying LP and Q estimates without having the result here, okay, which would be slow. Okay. And then these bilinear estimates, there's a nowadays a standard argument in transfer them to linear, developed by Tau, Vargas, and Vega, and that's how they can give the results. And nowadays there are trilinear estimates, multilinear estimates that we'll show up later, that they can give even better estimates here, but I'll stop for now in this respect. So after this quick review of what happens in 2 dimensions, let's try to put in action this more difficult framework in 3. Okay. So and I'm going to start again by the fixed time estimate when time variable is still not happening. Okay. So if you remember in 2 dimensions, when there was no time, the argument was trivial, no? In 2 derivatives directly, and then in L infinity is trivial because it's an averaging, and one interpolates. Full end of a story. No? However, here I have three dimensions. What I know is that these 3 derivatives of this span. So I could try to do the same. No? I can say, okay, I think in general for an arbitrary point, I do van der Kolk now with 3 derivatives. Okay, and then I get freeze decay, 1/3. Okay, and those are the L2 estimates. Okay, and there are infinity estimates I could interpolate, and that's it. However, this turns out to not be the optimal thing. The examples, they were conjecturing that one should be able to obtain still 1/p, not from 2, because for 2 is impossible, because in 2 we have 1/3, we cannot improve that. Okay, but maybe for p larger, doesn't matter that it's 4, or some other p, we close to it, for p close to infinity, maybe we should behave like that. So how could we improve that? Okay, and here the key is that I only should use 3 derivatives in the oscillatory integral if the first 2 are equal to 0. Okay, because if for some reason the second one was not equal to 0 and had a lower bound, I should be using the second one. And the second one gives a better estimate. No? So these 3 derivatives, this decay should only happen in a specific region of my space. And it happens when these 2 are equal to 0. The first 2 equations. And that gives me, I have here 1, 2, 3 variables, the psi variables, and I also have the S, the extra one. So 4 minus 2, it gives me a 2-dimensional surface in R3. Okay, so, and it turns out that it's a cone, like similar to the one that appeared later. It turns out that it's a cone. So this is like the singular cone. Here things are bad, that means that they have this decay. However, if we start moving away, okay, then we should have improved estimates instead of this. Because moving away means that this is not going to be 0. This being 0 doesn't happen anymore. So this has a lower bound. And when we are farthest away, is that this is bounded below by the size of psi, no? the magnitude of the frequency. Okay. So in here, we should be able to use fully second derivatives. Okay. And then in between, like an interpolation between 2 cases. So one can implement that quite efficiently, because then one can control here, one can quantify how close we are to vanish for the second derivative, and then get an estimate by using 2 derivatives, okay, depending on that parameter. So we can quantify how, when we are in between the 2 decays. And again, this is equivalent to localizing here to a certain to the critical point in S, but doesn't give an L infinity gain. So if we want an L infinity gain, we do the same thing as I introduced earlier. We break into pieces. That gives you a better L infinity and gives you a better LP bound, no, by interpolation. And this gives the very same picture as before. No? This gives that breaking into L infinity is breaking again these cones into these kind of plates, okay? And the question is how to access them, no? And you access them using, again, these decoupling inequalities. That I presented the square function, also the decoupling. In this case, the decoupling is enough to give the sharp result, and that was observed by Pramanic and C. Okay, but in here, what we have is a family of cones, no? So you apply it not just for a singular cone, you apply it for all the ones as you move away. And you can see that when you are farthest away, there is no decomposition anymore because it's not. You could use now the square function, but only now, not back in the days. Yeah. Okay. So what about the local smoothing estimate? No. So now we want to integrate in time. No, and we want to get some extra gain. No. And let me present the two extreme cases. No. One is L equal to 0. L equal to 0 is when we were away from the singularity for the fixed time estimate. No? Here there is no time yet. But if we just look at the psi variables, okay, we have two extreme cases. Singular cone, which I'm going to denote by k/3, okay, and away from singular, which I'm going to denote by L equal to 0. Those are the two behaviors. Okay. So now I want to introduce time variable to my problem. And then let's look first what happens away from singularity. So away from singularity, now I do the same thing. I take Fourier transform in time, as we did earlier, okay? Because I have now a problem. The new problem depends on time. So I would have a tau variable, which is the Fourier variable. So I look again at the critical points for that new oscillatory integral. And away from singularity is that this second derivative was not vanishing, that was bounded below by the size of frequency. Okay, so I only have these two equations being equal to 0. Okay, and that gives me now a three-dimensional cone in arc form. Okay, because we have the time variable, so it's like we've gone up one dimension. Okay, so somehow this case is if you think of like when we were talking about 2 + 1 dimensions, when we talk about the circle, what I started with, okay, the conditions were also second derivatives are bounded below, and these were the ones equal to 0. The only difference is that we are now, everything is lifted one dimension. Okay. But the conditions and derivatives, they are the same as this is the non-singular case of this problem. They are the same as in the previous dimension in terms of behavior of derivatives. So one can think of as that there are is a cone with two flat directions, and that by projecting somehow we can use the results by one dimension less. And that's how Pramanic and Sear dealt with this case. The projection is very complicated. They have to be an iteration in order to see the projection, because there are not flat directions. But for the purpose of this talk, the idea is to use techniques from one dimension less and to lift it to one dimension up, because the behavior is the same at a quantitative level. Okay. And then there is the other case, the most singular region. Okay, the one corresponding to that red cone. Okay. So in there now, I have the two conditions from before, okay? The tau condition and the gamma prime condition, but I also have that this vanishes. I have to use third-order derivatives. So now I have three conditions. I have an extra condition, I have a cone in one of one less dimension. And this cone of one less dimension is inside the previous cone. Because if I just drop this condition, then I'm in this other manifold. No, so is this singular cone now in 4 dimensions is inside the one coming from here. Okay, and one can actually solve with what is this cone, no? And this cone is now a generation over a moment curve, like a conic moment curve. Okay, it's a 2-dimensional cone, and if you remember in the previous case, in 2 dimensions. We have, this was the circle, and we have essentially a cone over the circle. But it was tilted in this way. No, I think that it was tilted in this way. But this is the picture in mind. So now it's the same. Instead of a cone in 2 dimensions, what I have is a helix And it's like, I have like a cone over that helix. That would be the picture. Okay. So that is the geometry, no? So this is the picture that we have. So now this is my spaces are four. This green manifold corresponds to the three-dimensional cone, okay? From the case L equals 0, right? Let's say. And inside here, we have the previous cone, singular cone that we have in one lower dimension, that now it has originated a two-dimensional cone in R4 inside the previous one. No? And then I have all these intermediate pieces. It's like I am always inside the green one, but I move away from the red one. Okay? That's how the situation has evolved. So in here, this case is the one where the two-dimensional cone dominates. No? This case is the one where the yellow one would be the behavior in the yellow region. No, it's like it's the green region, only the green region. I don't see this one, I'm too far. And then in between, like both geometry should be taken into account. Okay. And the work of Pramanik and Seeger, where they were giving this partial result for the maximal function, what they did was a very good analysis of that piece L equal to 0. And as I said, they were doing it, thinking of it as a sort of projection at the right scale, and using the theory in one lower dimension. Okay, and their analysis, which was very effective for this piece itself, it can also still continue. It can be extended to these intermediate pieces. Okay, but when extending it to the intermediate pieces, it becomes less effective. And that's what gives the restriction, because we would like to go to P equal to 3. But because they only analyze this part very effectively, but not this part, okay, then they get a restriction as soon as the method becomes more inefficient. Okay. You can see in here, the picture would be that when you are in between, then you want to have a decomposition according to this cone, okay, but then also to the other cone in 2 dimensions. But this would be how to. I don't want to go into those details because I want to go to another. And then the work that we did was to instead do the opposite extreme that they were not analyzing, no? To go to the other singularity. So their analysis was good enough, as I said, for L equal to 0, but also for a little bit in an extended range was enough to go down to 3. And then what we did is to study very effectively, that was with Guo, Hinman, and Seeger, study very effectively what happens in the most singular part. Okay? And then our method becomes less effective as we move away from the most singular part. It's like what we take really into account is the 2-dimensional manifold, and not as much as we are embedded in the 3. No? And then it becomes to be less effective, and it becomes total rubbish when we are super far away. Okay, but then when we are super far away, we have their analysis. No, so then the two methods merge, and then they complement each other. So in the proof of the maximal estimate, we are still depend on their previous result. Okay. For the extreme part. Okay, and here when we are in the most singular part, so the game is to try to do when we are things localized here in this cone, no, to try to do the same game as we were describing in 2 dimensions, but try not reproduce it in 3. Okay, for the singular part. So to break into the right pieces where we have good L2 and good L infinity estimates. No, L infinity estimates. This is the same. Saying LP estimates and saying kernel good pointwise kernel estimates is effectively the same. No, so that's where we that's what one does. This is exactly the same thing as before. No, before we had these plates in that previous geometry. Now we have similar plates here in this more difficult conic helix. But then what one needs to understand is we understand these pieces independently very well. Can we look for some orthogonality as before, no? And try to explore the methods of decoupling or a square function estimate or something like that. Okay. And then in this case, the decoupling estimates, they are not effective, but what is effective is to implement the strategy of square functions. Remember, square functions, they are still keeping some interaction between the pieces. So if you get some sharp square function here, then after that, the method developed by Max and Fasiger itself is very effective. I'm not going to go into details because I have no time, but the key is to get no loss here. Okay. And this we were able to obtain adapted to that geometry. Okay. So the proof of that for the ones that are a little, maybe have seen proof of the square functions before, despite this is L4, this is way easier than this good Wang-Zhang thing that has been solved recently. Okay, that has been a milestone. This is more similar to a previous L3 estimate of Lee and Vargas in one less dimension. Okay, so here we always want to go from L2. We want to keep this in L2 would be trivial, no? Because these are in Fourier side, these are disjoint, no? Okay. So in L2 is always trivial, and what one wants to do is to push the P as much as possible. So we are able to, and in 2+1 dimensions, before the recent L4 estimate, it was possible to push it to 3. Okay, and in the analog of that pushing it to 3 is pushing it to 4. Okay, and that's what we do. So it's not as difficult as the new developments. And in here we use essentially the same method of Lee and Vargas. In their case, it's trilinear estimates because they are in R3. In our case, it's linear Fourier restriction estimates. Okay, but for two-dimensional surfaces, because we have a two-dimensional cone. We have this helix in R3, and we have a cone generated by this helix. Okay, so what we do is for linear Fourier restriction estimates for two-dimensional surfaces. These are not the standard Bennett-Carveri tau estimates, but because those are for hypersurfaces, but they are more recent ones developed by Bennett, Best, Flock, and Lee, where they have done it for intermediate dimensions. Okay, and when one has this L2 estimate, there is a trick. There is a trick by Bourgain to transfer this L2 bound here as a square function. And once you have the square function on the right-hand side, you have a multilinear square function estimate that you can run the Bourgain-Guth argument to turn it into a linear estimate. And indeed, in the form by Shechion and Sanjik Lee, because this is for curves. Okay. So this is like the scheme for the L3 estimate for the top. So once one has that, then one can apply this square function estimate with no loss. And typically, how one takes advantage of this interaction between the pieces is by duality. One can pair this with a weight, okay? And then I have now this pointwise, the pointwise multiplier acting on my function, and one can use the kernel estimate that I showed before. That for these pieces, this is like the LP estimate, but in a kernel sense, no? So so they come with the right gain of 2 to the minus k over 3, because this is this is a localized till infinity, and until 2 we always get that gain. Okay, so so then one throws that into the weight, and how one closes this argument. This is this Markov-Hossidel-Sock argument. Is one takes Helder, and that one ends up with a square function, but for a localization in a lower dimension, and with a maximal function here acting on the weight, but this maximal function is on L2 and it's not on L3. Okay, so so this square function to put pieces together is a classical result of Cordova, and this other one, this L2 maximal function on this maximal function on L2, because it's L2 and it's not LP, one can use Fourier methods, and it can be treated with standard results in the more standard theory in the literature that I'm not gonna comment to. That's how one treats the most. In a very in a very sharp way this singular cone that we had, then the method starts to become less optimal as we move away, but still okay for the purposes. And another things are set up. Let me comment that there was, as I said, there was another proof of that maximal estimate that by Coley and all, they came out independently, and also the methods were different. Okay? So their method in a very summary, okay, what they focus is they don't focus on the two-dimensional cone, as I said, as much. They focus more on the three-dimensional cone, on the bigger one, okay? But they do a different analysis from this Pramanik Seeger, where they were kind of projecting, no? They do a real analysis of this in R4. And what they do is they do directly Fourier. They realize that these cones, they are not C2 hypersurfaces, but they are like C1, 1/2. They have mild irregularity, but they can still extend the Bennett-Kerbery tau estimates to this setup. And they have this multilinear estimate. And with using multilinear estimates, they can transfer them to linear, and they can prove it. But they use strongly the setup of the three-dimensional cone, but very differently from Pramanik-Seeger. Instead of projecting an argument in a lower dimension, they do it in the right dimension, no? In the dimension where they live, no? And that's how they approach it, and that's gonna be relevant. They use, as I said, the Burgan-Guth or Lee-Ham argument to transfer to linear estimates. And when I go to the LP-LQ estimates, where I started to extend it to the other side. Now, what we want is to get this improved estimate, but for this triangle that I pictured. And what we in the result with Duncan and Hickman, what we did is, okay, the corner is an L4 to L6 estimate. Okay, so if in the corner I don't obtain it, I obtain it with a little loss, with an epsilon loss, because on the diagonal I had already what I just described. Okay, we have them with an epsilon gain. Then by interpolation, as soon as I move away from that corner, then I have it on the interior of the region. So we focus on obtaining something for the critical point for L4, L6, and this is why we don't obtain anything in the bottom. Okay, because in L4, L6 there is here a little loss. Okay. So this, and in order to hit this 4/6, what we try to do is to do something similar as these bilinear estimates that were used to prove LP-LQ estimates that I presented earlier. These bilinear estimates of Wolf and Tau, the way they were used by Sanchuk Lee to obtain the LP-LQ estimates. We try to do the same thing. And remember before we had here there would be a triangle, no? This triangle would be the one that we are interested in. Here we need these bilinear estimates to hit that line, no? So now we try to do something similar, no? We try to go to trilinear estimates to be able to hit this critical point. No? In this diagonal is like the previous analysis that I just described. They give you something sharp here that we can use as a point to interpolate. So here there's some trivial estimate. The right thing is to try to hit a trilinear estimate. So, but the trilinear estimates that we use, they are so-called trilinear localized estimate, and I'm gonna refer to that because here there was already a 4-linear estimate. The 4-linear estimate that I presented with the Coley approach. No, I said they use a 4-linear estimate for these 3-dimensional hypersurfaces. No, but here there is a trilinear estimate which is a little better. Okay. So we combine both strategies. The Coley approach, they were doing this three-dimensional cone, okay, cones in R4, and that's the geometry they were using. Okay, the approach that I presented here, what we were using was just this cone, but not the big one. Okay, just this one. So what we do in order to obtain these improved estimates is to kind of combine both ideas. That we are working here, but we also have another 2-dimensional cone. Okay, so let's see how to try to do that. This is the estimate. This is an improved estimate, and I'm going to explain what improved means in a second. So we have hypersurfaces, but one of the functions, or even the three, but we are not going to use the three, have certain localization to a two-dimensional code inside the hypersurfaces. So in other words, the four linear estimates here, they were using this green one, and they were not really using as much that we might be localized in a neighborhood of this. Okay, and so we try to get some gain from this. Okay, in the argument. And let me put that, and this idea is due to Beltran, the idea of trying to get a gain. And it can be put in a broader context. So, and for that, let me just go to this general framework of the Bennett-Carr-Tau estimates. We take the Fourier extension operator, adapt it to hypersurfaces in R. And their theorem says that if we have hypersurfaces and we have the normals, they span, okay? If the normals span, then we have this multilinear estimate, okay? And we can take as many factors here as we want with k up to d, okay? And then we get an exponent depending on this number of factors. Okay, so if just as an illustrative example, we have the paraboloid, okay? If we have the paraboloid in R3, for instance, we have three patches of the paraboloid. These normals, they span R3, so that could be a good situation for this type of like trilinear interaction between three pieces. Okay. However, imagine that now one of the functions is localized to a string. We should think of these as like O of 1 pieces. Okay? But imagine that now one of the functions is not living in an O of 1 piece, but is here really concentrated on a mu, let's say mu is a scale, okay, mu neighborhood of a line segment here on the parameterization domain, which means here we have a curve inside the paraboloid, and we have here an extra localization. Okay. So now we don't have if we just take the core curve, the central curve, okay, we have not just one normal, it's a curve in R3. So we have the normal space is two of that, no? So now we have two normals, another normal, and another normal. I have four normals. Those four normals, they cannot span R3. They are too much for R3, okay? So I need to remove one of them, no? So if I remove one of them, I still have 1, 2, 3. If they span, I have a bilinear estimate, but this is localized, a bilinear estimate for an extension operator localized to a curve inside the paraboloid, and extension operator with the piece of the paraboloid. Okay. So in general, the setup is that imagine that I have an S1 prime submanifold of S1 of codimension M. And I have that one of the functions is localized in a neighborhood of this S1 prime. So then the extension operator to the S1, I can write it as they are extension operators of the curve translated of many copies of the same curve. Okay. I have one variable which is giving me the width of that neighborhood of that curve. Okay. For the curve would be the case n equal 1. So then when I try to estimate the multilinear estimate, I could just use this, no? I could just go to the extension operator adapted to the sub-submanifold, okay? And then interaction with all the other ones at the hypersurfaces. Okay. And now I have this integral here. I have this 2k over k minus 1, and I wrote it as a geometric mean, 1 over k. Let me rewrite this as a 2 over k minus 1. Okay. And so imagine for a second that this exponent was greater than 1, so that I can do Minkowski. Okay. That's the case in dimension in bilinear and trilinear. Okay. If I can do Minkowski, I could pull this inside, and the integral in the mu is outside. And then I have now interaction between the sub-submanifold and the other hypersurfaces. Okay, and if the normals span, as I said before, then the normals span with the new sub-submanifold, then you have a multilinear estimate coming from the multilinear estimate theory. Now I still need to put this function together with the extra variables that I haven't used, no? So in order to put it in L2, I need to do a Cauchy's bars. And when I do a Cauchy's bars, I pick up the size of the support. Okay, so this size of the support is telling you that you have an extra gain compared with the usual Bennett-Carveri tau if you have this localization. Okay, so this type of estimate was introduced by Bezenaru. And in general, you cannot do the Minkowski trick because you can only do it for bilinear and trilinear. So what he proved was an argument to do it in general without that trick, and I had to work out a real proof. No? And we have an upcoming work generalizing the case actually. And here the setup for us, it looks precisely like that, no? Because we have some hypersurfaces, which are the three-dimensional cone, but we are also localized near a two-dimensional cone. So we have exactly the same setup as this localized estimate of Bezenaru. So there's an improved estimate taking into account the support. Okay, and that's what gives you an extra gain that for the PLQ estimates it was the missing new ingredient that was needed to analyze this type of arguments. And indeed for us, because it's a trilinear, the Minkowski trick works. So we don't even have to appeal to the Bezenaru result because it's trilinear. And that turned out to be more effective than the 4-linear estimate of Coliano for the purpose of the PLQ problem. Okay, so that's it. And I want to finish with this nice picture that they sent me on the weekend when they were not in Porto. And I want to say decir obrigado al grupo de aquí por tratarme también estos días.